Can you see the screen?
Yes, sir.
So in that part, initially we were doing about the free vibration response and the solution of the equation of the motion, that how we can make an equation of motion for the different system. That was basically already covered. And in that part, you know that there are three components for the equation of the motion. And for undamped free vibration, how can we solve those? We can take the solution of the equilibrium equation as u is equal to g general solution, and then second derivative and the first derivative, and apply the boundary conditions to those to find out the value of unknown parameter g. In this only g is used because damping is absent, so that's why this is undamped free vibrations. And from here the one relation is also proved, that is omega, the circular frequency, which is equal to under root k over m. And then the undamped free vibrations for the equation of the motion we can write in this form, g1 g2, and it can also be cos of omega t and b sine of omega t. And these a and b can be determined by the boundary conditions. So these are the constants, and this is the first solution for the undamped equation of the motion that we have done in the class. The first one solution for undamped free vibration. And this solution can be written in this form, which is like u, and where this rho is the amplitude, the maximum value of this undamped free vibration, the maximum value of the displacement. And phi is basically the phase angle, that is angle formed for at different points in this one, that when it is started, what is the angle of this one with the horizontal. So phi is the phase angle, and the time period is 2 pi over omega. So let's say you have the displacement at any one instant, so time to complete one vibration is 2 pi over omega. And for hanging spring also, this was the problem, where for hanging spring, what will be the displacement? Delta st. So W is equal to mg, where W is also equal to force is equal to kU. U is delta st, and we know that W is equal to mg. So this implies that mg is equal to k delta st, and k can be computed. And omega is equal to k over m. Now putting the value of the k here, and we can get the value of omega for spring. We need the g value and delta value, and we can determine its frequency in radian per second. And from that we can determine the time period, because time period is 2 pi over omega, and then from that we can find out the frequency value. When you plot the diagram of this undamped vibration, it's like that. But when you plot the diagram of the u and the u dot over omega, how we can compute the u dot over omega? We can compute by taking the derivative of this u. The u for undamped system is rho sine omega t plus phi, and we can take the derivative of this and then divide by omega. It gives us the rho cos omega t plus phi. And if you plot these two values, this is basically the u dot over omega, and this is u. You get the circular, because there is no damping. So this keep on the the graph between u and u dot over omega is a outcome is a circular, and phi is this one here, the phase angle. Rho is the maximum radius of this circle become the amplitude, the rho value. And when you plot the graph between the u dot over omega and the time, then you will get this kind of graph. It is a derivative of the displacement. So initial value will be v naught over omega in this case, and here the initial value is of course u naught. So this graph is plotted between u naught over omega and time. Similarly, the other case when you have the u here both were present, u and u dot, but here in this case the velocity is 0. Initial velocity u v naught is 0. So then if you plot the graph, it will be like that. It is on the circle, but rho is the maximum value normally at start also, and it's basically radius, and initial value is basically equal to 0. And when you take the derivative of this derivative, or u dot over omega we compute, we can see that initial value is of the u dot over omega is 0. So this is the curve function between the u dot over omega and the time. And this is the case when the displacement is 0 initially. When the displacement is 0, then when we plot it, and velocity is not 0. Velocity is present. You can see here that we can determine the slope of this line initially. So u dot over omega will have some value here. This is shown, but u dot is 0. Then we get this kind of graph where the rho is the maximum value at this x-axis, and the remaining part is u dot over omega. If you plot, this is not 0 at the initial stages. And sometimes there is an impulse that this is a regular motion, but initially due to some impulse effect, the impulse which is equal to the mass and the velocity, there is initial value also. And when we plot that and on the displacement and time scale, the impulse is generating one extra wave, and that when you take the derivative of this, because now the impulse in the amplitude I over m, the displacement due to the impulse is also added. So that's why this additional is obtained at the top because of this impulse. And when you derivate it, the impulse gives us this behavior. This is the additional force basically when acting in the regular free vibration. In case of ground motion, when you have the ground acceleration is there. Initially, the ground displacement is there, and initial velocity is 0. Ground acceleration is there. So in that case, the total amplitude is equal to the ground acceleration, and our phase angle become equal to 3 pi by 2. So it means that the phase angle is here. At this point, the amplitude is obtained, and total displacement is ug plus ug sine of omega t plus 3 by 2. This is the total displacement. Generally, it can be written in form of u is equal to ug 1 minus cos omega t. And when we plot the ground displacement as a function of the derivative of this ground displacement, I mean u, where the free vibration start due to the ground vibration, this kind of curve is obtained, which is 0 at the start and then it varies. similarly like the previous initial cases. So these are the problems. One is a steel frame problem that was discussed to that if there is a steel frame and free vibration is there, determine the natural frequency of the system. So this is a frame and we can determine the properties. These properties are given. You can determine the K value. K is 12 EI because E is there are two columns, so 2I over L cube, and K is computed. From the K, you know that F is equal to 1 over 2 pi K over M, and M is equal to W over G. So K is also known, W is also known, G is 386 inch per square second. So frequency can be computed. The second one, the problem of the overhead tank to compute the properties of the tank under the effect of free vibration. The elevated tank will be of this gallons is shown in the figure, and as a natural period in the lateral vibration of 1 second when empty. When empty, it has the natural period of 1 second, and when tank is full of water, its period is 2.2 seconds. And we have to determine the stiffness, weight of the tank. These two items are needed. So the case of the this can be represented by the spring mass system. And then you can compute the omega value for empty case, omega E value for empty case, 2 pi over TE. And the second case is the weight of water. Second case is the weight of the water that is computed because 5,000 gallons in pounds, and when the tank is full, the omega F is 2 pi over TF. But here the total weight will be the sum of the weight W and weight of water, and weight of the tank is W. Now in the both the cases, first and the second equation, we can divide the first by the second equation and then taking the square of both to finish the under root, we can determine the W value, and putting where the W value in this any equation, we can get the stiffness value also. So this was about the free vibration, and I asked to work on the MATLAB and plot some free vibration response. One of the example was solved here where the free vibration response was obtained. Next part is the damped free vibration, which was also lecture was provided. So damped free vibration. Here C is not equal to 0. You can see that C is also present here. And the general solution of the displacement can be written as G e raised to power lambda t. Now you take the derivative, second derivative, first derivative, u value, put it equal to 0, and then G is cancelled, and you can find out this equation for the damped free vibration. And from that you can determine the roots of the quadratic equation. Lambda is basically this factor variable, and you can have the roots. But now there are different cases of the discriminant. The discriminant is equal to 0 or larger than 0. So actually that is linked with the damping coefficient C. Three different cases are there. When you put the root equal to 0, it is a critical damped system. C is equal to CCR. And when you put the value of the root larger than 0, it is an over damped system. And when we put the values of the root less than 0, it is under damped system. Most of the civil engineering structures are under damped system. So from that you can determine the damping, critical damping value also, because the critical damped system you put it equal to 0, it means that C becomes CCR critical, and that will be equal to 2 under root km. So 2m omega is the formula for the critical damping. When we put it larger than 0, it means that C is larger than CCR. Or you can say the damping ratio zeta is equal to C over CCR. The damping coefficient over critical damping coefficient, that will be larger than 1. And in case of the underdamped system, the ratio of the C over CCR, or the value of the zeta, will be equal to less than 1. Most of the structure you know that the damping coefficient is less than 1. This is the vibration response, free vibration, under the effect of the damping. We can determine the values of the roots for all the damping cases. This is a general damping case scenario, and here we can put down the value to find out the roots. So there are now the three cases. For critical damped system, the response will be different. For the under damped system and for over damped system, the response will be different. That's why the three different cases of the U are provided here. First one is for the critical damped system. When you put it equal to 0, the discriminant, and C is equal to 2m omega, because C is equal to C critical. And here both the roots will give the same answer, omega, and when we put the value of the lambda as omega minus omega t, and by determining the initial conditions, putting the equal to u and the u not equal to 0, to find out the unknown constant g1 and g2. G1 comes out to be u naught, g2 comes out to be v naught plus omega u naught t is here. So this is equal to the u value for the critical damped system. And what is the result? That the critical damped system, when you plot the critical damped system u as a function, you see that it is suddenly there is no vibrations. It's the example is the recoiling gun and weighing scale. Free vibration of a system is not oscillatory actually. And after the initial disturbance, the system will come back to its original position without oscillation in the maximum time. So very small time, the system come to be in original, in normal position. This is a critical damped system response. And when you go for the overdamped system, then of course the zeta is involved because C over C, I told you is larger than critical zeta is larger than 1 actually. So in that case, you can put down the value of the C and 2m omega, and C is this one. Now the roots of the equations can be determined. Lambda. Here in this case, the discriminant is not 0, so it will be present, and omega is there. So we say it omega into zeta square minus 1 as omega bar. In this case, we call it as omega bar, and omega bar is equal to this one. Now we can write down the solution of this equation of the motion by putting the roots and by putting the initial conditions. The response of this system is shown by E minus omega zeta t, a hyperbolic function of cosine cos of omega bar t, and B sine of the omega bar t. So its example is a automatic door closer. That it's a overdamped system. It slightly lies lower than the critical damped system, and it's suddenly the amplitude of this system diminished. So this is the formula, the last one, which is used for the plotting the functions of the overdamped system. Normally there are not much structures actually which lies under the overdamped or the critical damped conditions. Normally the most of the civil engineering structure lies under the underdamped condition. This is the underdamped case when your zeta value is less than 1. What happens when you solve the root here? This root, because this value will be less than 1 discriminant value, so iota will be there because the answer will be in minus. So we put the iota outside that, and generally the lambda can be written like that, where omega d is equal to omega into 1 minus zeta square. In this case, this is the omega d. D for the underdamped, because it is an underdamped system, so we are denoting it with the d. And the general solution of this case will be written as this one, E minus zeta omega t into A cos of omega dt plus B sine of omega dt. And A and B are determined from the initial condition. A is equal to u naught and B is equal to, comes out to be this. This is the solution for the underdamped system. We have the omega d value, which is omega into 1 minus zeta square. These are known. V naught, u naught are the initial conditions, and zeta omega t, these are known. So e raised to power, so exponent, we can use this function in the MATLAB or anywhere, and we can plot the u value. So what is the now comparison when you have studied the three relationship? One, the third number, that is the for the underdamped system, one relation for the overdamped system, and one relation for the critically damped system. So if you join all these relation and plot against the time, you see that the critical damped system, it's like showing the no oscillation. Overdamped system, again it lies below the critical damped system, and underdamped system with damping, it is show the more amplitude initially, and then its amplitude is reducing and it shows the oscillatory motion. But with time the oscillations are reducing and it will finish at the end. So these are the function. Normally if you plot the rho e minus zeta omega t, this line is obtained, the blue lines. If we just plot the e minus zeta omega t multiplied with the rho. But when we multiplied with this other function also, then again the whole damping, this oscillatory motion is seen. So this is the plot of the three motions, I mean underdamped, overdamped and the critical damped system. And most of the engineering structure lies with this underdamped system. Like initially the vibration is higher and then with time the vibration starts reducing. And this is the phase plan diagram. This is different than that one, the free vibration undamped, because there was no reduction of the amplitude, but here because the amplitude is reducing in every vibration, you have the initially higher value, then the second one, lesser one, and then the third one. So this corresponds to that. This plot is u and the u naught over omega, and this plot is u versus time. Now the logarithmic decrement, if you see that this is the first one, displacement u1 and u2, how these are reducing. So it is seen that these are reducing by logarithmic decrement. How logarithmic? You have the first displacement at ut1 and then the second displacement at ut1 plus 2 pi over omega d. And when you solve it, this also, and the first write down the equation, and then you take the delta, which is the increment or decrement actually. So decrement can be represented by log of ut1 or ut1. Both decrement can be represented by this way. Because it's when you solve these two equations and take the ratio, it is e raised to power that, and we can write actually rather than e raised to power something, we can write it as u of t1, that log of the displacement at t1 over that one. So that's why it is represented by logarithmic decrement, and its delta is 2 pi zeta over 1 minus theta square. This, if you solve it, this also comes out to be equal to this. So it means that from the two decrement, if you know the first and the second displacement, you can determine this difference of amplitude delta, and this is a zeta value. Damping ratio can be computed by, if you know the delta, you can compute the damping ratio also by delta over 4 pi square plus delta square. But for many practical cases of engineering, delta is less than 0.2. It means that 1 minus zeta square, this under root value is also equal to very small, closer to 1. And delta can sometime, for smaller damping value, the delta is 2 by zeta. It is simply, it means that zeta is equal to delta over 2 pi. Very small formula that if you know the delta value, this one, the difference, and then you divide by 2 pi, you can find out the zeta. Or you can say that the zeta value is equal to 1 over this is the general in terms of the for lightly damped system. For lightly damped system, when zeta is very small, the ratio of the first and the any other displacement, the logarithmic of that is n times the delta value. So delta is 2 pi zeta for small, so it can be written like that. Or you can say that zeta is equal to 1 over 2 pi n. From that you can compute zeta is equal to 1 over 2 pi n into log of u1 over un plus 1. For small value you can determine the damping ratio like that. So advantage of this curve, if you have the damped system, you have this successive graph for the damped system, you can obtain the damping ratio from that. If you have the first displacement, second displacement, or even if you have the first displacement and the last displacement, you can determine the value of this damping ratio. Normally it is seen that the number of cycles in which the amplitude will decay to half of its value at the beginning is given by 10-50%. Generally you can determine that the amplitude will reduce half of that value. That is the, you can determine that zeta value 0.11 over zeta, you can determine that n 50%. The number of cycles you can compute at which the amplitude will be reduced to half of this value by this formula, because just you put the 1 over delta log of 2, because the ratio we need the 2 value here, so we are putting the value. Why 2? Because we want the half of this number of we want to decay to half of its number of cycles, so that's why putting it to so n 50%. And if you plot the graph between the damping ratio and the number of cycles, you can see that as the damping ratio is increasing, the number of cycle to reduce the amplitude up to the half of that are also reducing. So there, this was the theoretical part, and there are examples also related to that. Herein we are applying this damp free vibration to some structures. So you can see that a free vibration test is conducted on an empty tank. A cable is attached to it, applies a lateral force of this skips and pulls tank horizontally by 2 inches. The cable is suddenly cut and resulting free vibration is recorded at the end of the force cycle. The time taken is 2 seconds and the amplitude is 1 inch. First it is pulled by 2 inches, but at the end of the force cycle, the time 2 seconds were needed and 1 inch is the final amplitude. So you can say that it's like free vibration test is conducted on the empty tank and it has this 4 vibration, and at initially it was 2 inches, here it is a 1 inches, and there are 4 cycles and 2 second time was needed. Now you can compute the damping ratio, the natural period, just by this data. You can compute the stiffness, you can compute the weight, you can compute the damping coefficients, and the number of cycles required to reach the amplitude 2.2 inches. We also want to compute the number of cycles. So these all are possible, that if this tank is keep on vibrating, how many number of cycles are needed so that the amplitude will come equal to the 0.2 inches. First step is to get the zeta value. We know that the zeta for the small damping is 1 over 2 pi n log of that we studied at the last formula, and we can un over un plus l. So what is the 2 pi into n is the 4 and log of 2 over 1. Initial displacement was 2 inches, the last was 1 inches, and number of cycles are 4. So 4 value, 2 and 1. And we can determine the damping ratio. First problem. You can also determine the, because length total number of cycles are 4, the initial displacement was 2 inch. After 4 cycles, the displacement is 1 inch. You can determine this zeta value. You can also determine the stiffness value. F is equal to kx, so k will be equal to F over x, where F is the force and x is the displacement, so the stiffness can be determined. And the damped period of vibration, time period, you know that time is 2, so 2 divided by 4 is 0.5 second. So 0.5 second is the damped period of vibration, and from that you can determine this omega, that is 2 pi over t, so radian per second you can determine also. Now you know that weight is equal to mg and omega is equal to k over m, so you can also determine the k over m under root. We can determine the k omega square, and this is the mass of the system, k over omega square, 0.0518 kip second square per inch. So this is actually omega. This one is due to the symbol, it's omega. So we can determine all the properties of the system, and from that you can also compute the damping ratio, because you know that the damping coefficient is linked with the damping ratio by this expression. Zeta is equal to c over 2m omega, and c can be determined now. The damping coefficient 2 into zeta, that was already determined, and m omega. So you can have the damping coefficient. Cycles needed to reduce to amplitude 0.2 inches. Now you know that zeta is there. Number of cycles needed, n, is now unknown because the initial displacement is 2 inch. The final displacement is 0.2 inch, because we want to compute now the number of cycles n which are needed to reach to the displacement 0.2 inches. So n is unknown, and we can determine the n as the 13 cycles. There are the different other problems, which are the second one, where a platform is being supported by 4 equal columns that are clamped to the foundation as well as to the platform. Experimentally, it has been determined that static force of F is equal to 1000 pounds applied horizontally to the platform produced a displacement of 0.1 inch. It is estimated that damping in the structure is of 5%. Determine the undamped frequency, absolute damping coefficient, logarithmic decrement, number of cycles. This is a similar kind of problem. It's like this.
5% damping का क्या मतलब? 5% critical damping.
जी
सर इसको जरा एक्सप्लेन कर दें 5% of critical damping इसका क्या मतलब है?
यानी कि आपकी जो डैम्पिंग है वो जीटा 5% है. जीटा वैल्यू है ना 5%. This is a platform. This is a 4 kip value. A horizontal load is applied of 1000 pound. Now we have this total weight. The lateral force is applied. This platform is resting on the 4 columns, equal columns, and it has been determined that a static force of 1000 pound is applied horizontally. Now you can compute the stiffness F over delta. Because force is 1000 is applied, the delta, the horizontal displacement is 0.1 inch. So this is a K value, and undamped natural frequency is kg over W. This can be determined as the undamped frequency. In the second part, now the critical damping, you know, that is equal to 2 under root Km that we see in the today expressions, and you can determine the critical damping value. And it is told that the damping coefficient is 5% of the critical damping. Damping is the absolute damping is 5%. So it means that 0.05 into CCR. So CCR is known, and if you multiply the zeta value with the CCR, ये damping की value आ जाएगी हमारे पास. Damping coefficient एक चीज होती है, एक critical damping है, और एक है आपके पास zeta, जो कि दोनों की रेशियो है. Zeta is equal to C over CCR. जहाँ से हमने CCR निकाला वहाँ से C निकाल लिया, because zeta was also given. Now the logarithmic decrement, the delta log over the initial value or any other displacement. For small damping, we have studied that it is equal to 2 pi zeta. For small damping, it is equal to 2 pi zeta. So you can put the value, take the value as this one, 2 pi zeta, and get the logarithmic decrement. And in this way, you can also compute the ratio of the two consecutive amplitudes, U0 and U1. U0 and U1. You can take the ratio of these two is 1.37, because delta, the decrement is 0.314. Taking the anti-log, we can get the ratio of U0 and U1. Now the next one is the ratio between the first amplitude and this one. Also please see how the remaining steps are solved. जी क्या क्वेश्चन है? So ratio between the two can be expressed in this form: log of the any displacement to the next displacement, that is equal to k time delta. That is the ratio delta 0.314 is the one delta. So more number of vibration, so we can determine that, let's say the initial was 10, the final rate decrement delta is 0.31. This k is not stiffness here, this is the number of cycles, that how many number of cycles are needed to reach to the vibration 0.314. You can directly use this expression also that we used in the previous here, this one. If you know the zeta value, you can determine the n value here, that how many number of vibrations are needed to reach to that level of the displacement. Because in the damping you have this this is given, so you can determine as much how many number of vibration required to reach from certain displacement to the minimum displacement. And the ratio of the two consecutive amplitude, the first one and the second one, can be determined also. But damp frequency is, you know that the omega and omega d is different. Omega is the natural period of vibration without the damping, and with damping it is equal to, if zeta is small, you ignore that, but if zeta is not small, you can say that omega d अब आ रहा है आपका 31, but the omega was 31 also, 0.06, यहाँ पे 0.02, so very small difference. ये जो 5% damping है, This is also very small damping. And the damp period of vibration जो है ये 0.2 सेकंड आ रहा है. So 2 pi over omega is the natural and 2 pi over omega d is the damp period of vibration. If the system damped हो, when the amplitude is also reducing, then this is the damp period of vibration. Then the time for 8 cycle. 8 cycle के लिए क्या time लगेगा? You just multiply the time period with 8. इसको 8 से multiply कर दें, क्योंकि damp period of vibration है, वाट साइकिल्स के लिए ये टाइम है. तो ये सारे जो पैरामीटर्स हैं you have determined, जो उन्होंने पूछे हैं कितने साइकिल्स हैं, डैम्पिंग कोएफिशिएंट्स हैं. So in this way you can determine all the required parameters. बाकी भी प्रॉब्लम है, I ask you to see all those and try. ये सिंपल है, इसको 2 केसेस हैं और इसको आपने खुद you can try it yourself also from the exercise of I think exercise problem है ये by the A.K. चोपड़ा का चैप्टर नंबर 2 का 3 क्वेश्चन. और ये एक और है कि हम सक्सेसिव जो एम्पलीट्यूड्स हैं उनकी रेशियो निकाल सकते हैं. यस, वी कैन डिटरमिन बिकॉज वी प्रूव टुडे दैट डेल्टा इज इक्वल टू जो है आपके पास 2 पाई जीटा और 1 माइनस जीटा स्क्वायर है, एंड दैट डेल्टा इज आल्सो इक्वल टू लॉग ऑफ दिस डेल्टा. ये भी डेल्टा है, इन दोनों को इक्वेट कर दिया. नाउ वी नीड the ratio of successive amplitude un over un plus 1. This is unknown, and we have this all this. इसको log को हम उस तरफ ले जाएं. First take the 2 pi there, 2 pi zeta और 1 minus zeta square. फिर log उधर ले जाएं, that become the exponent. So you can determine the e raised to power this. So e raised to power 2 pi zeta or 1 minus zeta square gives you the ratio of the amplitudes. So you can determine the ratio for zeta. अब आपने कोई भी zeta है उसकी ratio निकाल लेंगे. Next zeta, next value, because only zeta become unknown. So e raised to power 2 pi zeta divided by 1 minus zeta square. You can find out any ratio of the successive amplitude of vibration. This way you can find out the unknown parameters. This is a simple example. You can just see that, and easy because this is not difficult. You can have the solution also. You can by the same formulas, and these are used, and you are able to solve that. And next is the one case. This is a bit different. This example also is solved in the MATLAB program in your book, textbook जो हम use कर रहे हैं by the Mario Paz and Anil K. Chopra. So this is an example from the Mario Paz also. And the next one is that this problem. Sir? Yes?
Sir, screen stuck हुई है.
Where what you can see now?
सर जो लास्ट एग्जांपल हो रही थी.
ई रेज टू पावर वाला आपने सुना है, देखा था?
नो सर, वो उसमें जब नेचुरल लॉग लिया था वहाँ तक ही था, उससे आगे नहीं। जी सर, अब आ गई।
क्या आपको नजर आ रहा है? What you can see now?
जी सर, अब
ये
क्या?
Vibrating system consists of
पढ़े
weight.
जरा।
The vibrating system consists of the weight of W 10 pound.
So in this system, you can determine the frequency logarithmic decrement. K is given, and ratio of the two amplitude is also 1 to 0.85. So all the parameters are given, and we have to determine the unknown parameters. So we determine omega and f value, then delta can be determined, and zeta can be determined by this, and C, the damping coefficient, can be computed from that, and damped relation it also. Now the plot the same response with the follow the same example. How to plot the response? We will do it at the later. I will show you the method. This is another problem. A mass is at rest, supported by a spring and partially by stops. In the position shown, the spring force is mg by 2 at time t0. The stops are rotated, suddenly releasing the mass. Determine the motion of the mass. So initially the mass is at rest. It is partially supported by a spring and partially by stops. There is a stops. The spring force is mg by 2. The spring force is half, not full but half is the spring force at time t0, and the stops are, when the stops are rotated, this one, the mass suddenly released down. Determine the motion of the mass, equation of the motion for the system. So this is a problem, a general different problem, where you have the spring force mu by 2, the stiffness of the system ku plus mu by 2, and the downward weight of the spring. This is the free body diagram. So it is told that the total force, basically mu plus ku, that is equal to mg by 2. You can write down the equation here, that ku plus mg by 2 should be equal to minus mg. So mg minus mg by 2, it gives us the mg by 2. So this is the equation of the motion. And you know that the general solution of the equation of the motion is, this is an undamped system. A cos omega n t plus B sin omega n t. And this force is already given. So ut, this is the function of this spring. And at time 0, now determine the constants. Time 0 पे हमारा A आ जाएगा. When u naught is 0, and when u naught, इसको फिर डेरिवेट करेंगे तो u naught डॉट यानी कि वेलोसिटी आ जाएगी, तो वहाँ से b आ जाएगा. So a comes out to be minus mg over 2k, b comes out to be 0. So putting the value of a and b, we get the function of the u and t for this case. ये हम इसका function ले लेते हैं. This is the displacement function of this for this spring system. This is the ut response. ये आ गया इसका. Now you want to plot the response with the following damping ratio for this problem. इस problem के लिए जो response plot करना है, so you can plot the response. So this one is basically the same problem, response of the damped system. The same example is solved. You have the values stepwise. Can you see the book page?
Yes, sir.
Initially, the value of M and K and C are given. Damping coefficient which are computed are input. U naught is 1 and V naught is 0. In this problem, it was given that here you can read it. And then this is a comment line, the green color, the black color is the coding line. Omega जो है वो computed undamped natural frequency under root K over M. So SQRT, this function is used in MATLAB. Then you can determine the critical damping ratio 2 under the root K into M, and then you can determine the zeta value. Zeta is the ratio of C over CCR. CCR निकाल लिए तो यहाँ से zeta आ गया. Now the problem is कि different zeta के लिए आप प्लॉट करें फंक्शन. 4 zeta value 0.01, 0.03, 0.5 और 0.9. So for 1 zeta is 0.01, 0.5, 0.9 and xi value जो यहाँ पे आई है वो भी इसमें आ गया. तो 4 zeta के लिए आपको लूप रन करना पड़ेगा for I is equal to 1 to, and we get the omega d. Omega will change when the zeta will change, and टाइम पीरियड जो है वो भी, एंड फॉर वेरिंग टाइम भी वेरी कर रहे हैं 0 to 6 सेकेंड विद 0.01 सेकेंड इंटरवल। ये जितना भी आप मैटलैब में ले लें, मैटलैब इज बेसिकली कंप्यूटिंग फॉर ऑल। तो इसमें आप दो वेक्टर हैं, पहले हम फॉर चला रहे हैं लूप फॉर द 4 जीटा वैल्यू, और हर जीटा वैल्यू के लिए फुल टाइम के लिए फॉर ऑल टाइम वी विल प्लॉट दिस फंक्शन ut। तो ये फिर आप निकालेंगे उसका सब जो फंक्शन है विद इन द यू के अंदर आएगा ना, आर्गुमेंट 1 इज एक्सपोनेंट माइनस जीटा ओमेगा टी। जो फर्स्ट जो पार्ट है यू का ई रेज टू पावर माइनस जीटा ओमेगा टू, तो ई कैसे लिखते हैं मैटलैब में, बाय ई एक्स पी। जो ई रेज टू पावर है उसको हमने लिखते हैं मैटलैब में ई एक्स पी, तो ब्रैकेट आगे माइनस, ये पावर में चला जाएगा ई की पावर में माइनस जीटा। जीटा अब हमारे पास चार वैल्यूज हैं, तो आई आ गया इसमें, ओमेगा टी, और टी भी हमारे पास वेरी कर रहा है, तो हर वैल्यू के लिए ये आर्गुमेंट आएगा। आफ्टर दैट द सी इज कंप्यूटेड वी नॉट प्लस यू नॉट एस क्यू आर टी ओमेगा और ओमेगा स्केयर प्लस वी नॉट स्केयर, ये एम्पलीट्यूड निकाल दिया जो फार्मूला था एम्पलीट्यूड का इन द अनडैम्प्ड फ्री वाइब्रेशन, और फिर फाई निकाल लिया। फाई इज द टेंजेंट इनवर्स वी नॉट प्लस यू नॉट इनटू जीटा ओमेगा और ओमेगा डी प्लस वी नॉट। नाउ यू कैन डिटरमिन द मैक्सिमम वैल्यू ऑफ दैट एम्पलीट्यूड दैट इज सी इनटू आर्गुमेंट 1, वहाँ से आपका एम्पलीट्यूड आ गया, एंड यू का जो फंक्शन है ये मैक्सिमम, वी नो दैट द यू इज इक्वल टू c into this value into cosine of omega dt minus phi। तो ये जो फार्मूला आज आपने पढ़ा था अनडैम्प्ड फ्री वाइब्रेशन के लिए, the u is written there। now अब हर टाइम के लिए एंड एंड, ये उस लूप को एंड किया फार एंड, सो 4 टाइम जीटा के लिए the 4 vectors are generated for the u for every zeta value, and टाइम जो है वो इस टाइम के अगेंस्ट 0 to 6 second, and when you plot this figure you have the 4 different plot। फर्स्ट प्लॉट जो है वो फर्स्ट जीटा वैल्यू की प्लॉट की, फिर सेकंड के लिए की जीटा यहाँ पे जो है वो सेकंड ले गए, थर्ड वैल्यू आप देखें ना यू जो है 4 आया, क्योंकि 4 डिस्प्लेसमेंट डिफरेंट है, u3 जो लास्ट कॉलम है हमारा 4 टाइम आएगा, as the zeta is varying so we have the 4 u values in the last formula you can see। so now the 4 different functions are plotted। zeta was lesser, तो आपने देख रहे हैं कि जैसे जैसे आप डैम्पिंग बढ़ाते जा रहे हैं द फंक्शन इसकी डैम्पिंग क्रिटिकल से बढ़ जाए, उसकी एम्पलीट्यूड जो है वो नंबर ऑफ वाइब्रेशंस आर रिड्यूसिंग, so as the time for the same time the displacement response is plotted। So this was the damped vibrations under the effect of the damping and logarithmic decrement। आपने देखा कि कैसे इसमें रिडक्शन होती है। फर्दर इस बुक में भी फर्दर इन द इजी लैंग्वेज it is written in the Mario Pass, so you can also get an studied in this chapter and try practicing the other problems linked with this one also। ये problem हमने कर लिया था, तो there are some other MATLAB program, so try working on these also, and these are very similar what we have done, and please also see some problems from the other books। So that was the first part of the lecture. Next is the harmonic motion. So if you have some questions you can ask, and then we can take a break, and after that we start the harmonic motion loading। Okay, then you can have a break, and then we will meet again after 10-15 minutes. Okay, we will start with the next topic.
Right, sir.